Hey guys, how's it going? Welcome to another episode of Ferris Makes Demos. This is the first time I've streamed in quite a little bit. At least streamed demo scene stuff. I think it's been 2 or 3 weeks since I did this. This week I think is going to be maybe a little different than some of the previous ones. Basically, the thing that I'm working on is some tech for our 64K compressor. And this project is a bit hard for me to stream. And the main reason is that I have to keep a lot of it kind of under wraps. And the main reason for that is that one of the things that has plagued 64Ks for a long time is the fact that the compressors that we use, and this also applies to 4Ks and basically anything that makes PC programs smaller that we use in the demo scene, they're also very often used by malware authors. And as such, there's a bunch of details about this stuff that I don't really want to let out at the moment. I think the most important thing to not leak is the artifact itself, the actual compressor. And I'm a long ways away from actually finishing that. But still, the ideas that I'm playing with, a lot of them will translate, will carry over to whatever I end up as the final solution, the final, whatever I end up with at the end here. So, kind of trying to keep some of that stuff under wraps. Although I'm not like super crazy about it. The other thing is that I don't want to publish my results yet. Mainly the thing is that it's not really representative of where this project is going right now. Anyway, there's a lot of things with compression that ends up being really unpredictable. And you just have to kind of play with a lot of stuff. But yeah, Skeleton, that's basically the main problem, is that malware authors will use the compressor, and then antivirus scanners are like, hey, I know that compressor. I saw that on this malware a while ago. So yeah. Kulash, this isn't related to the ANS stuff, actually. This is going to be, what I'm going to do today is I'm going to probably explain a little bit about the ideas that I'm toying with on this particular branch. I actually have a lot of different configurations of things that can compress stuff that I'm working on for this project, because you don't really know what's going to work best until you can try a lot of different things on a lot of different intros. So I've got like a test set of executables, some of which I made, some of which are from other groups, and I'm usually running all of them and stuff. And I'm not going to show any of that output because, like I said, I don't want to do this stuff. A lot of this is F. Geeson-ish, considering that he did Crunchy, which is the compressor that everyone uses in the demo scene for 64K. Except Biro, I think he has his own, and some other people there. But yeah, so basically, gonna try to keep some of this under wraps, but I do, at the same time, I do really want to share a lot of this stuff. I think it's really fun. It's a really nice learning experience for me, because other than until the previous year or so, where I've kind of been working on our own compressor off and on, I haven't really done that much stuff with packing. So the main times I've been working on this project, I was doing so about a year ago, maybe a little more than that. Yeah, Tourist, exactly. So his packer is also identified as malware, and some heuristics that the different virus scanners will use, like the fact that it uses merge sections and some things, I can't really protect against. But in terms of protecting against people using this for malware, that is something that that I've thought about, and also some of the other 64K authors that I've talked to about this project have requested specifically that we be extra careful about that. And I think that's a good idea, at least for now. Maybe that changes in the future. Ideally, I would love to open source this, but that's how it is. But at the same time, yeah, I would really like to share a lot of this stuff. There's some really interesting aspects of it, like the thing that I've actually been working on most recently. So yeah, I was mentioning I worked on this about a year ago, where I did mostly just learning about stuff and playing with different kinds of compression and sort of laying the groundwork for this, and at the same time also doing a lot of the executable re-slicing stuff, because you have to merge sections, remove things that aren't going to be necessary in the executable. So there's sort of two sides to the packer itself, and then all the stuff that's around it. And I made probably most of the progress then. I also picked this up again around after revision, and that's when I was working on identifying different bytes of an x86 opcode stream. This is very similar to what Rig's doing in his packer, where it's basically going through and he actually does a transform where he goes through the x86 in the code section, and by identifying which kinds of bytes there are, he can split them into different streams based on some statistics in here and some observations that he's made. The way mine is working is I think it's gonna use this information a little bit differently, but there's still this piece of it, which is what I've been working on recently. And stuff like that I could definitely release because it's like standalone components. But we'll see how it ends up getting used. But it's really nice to see this. Basically what this is a color-coded version of the output. So the mechanism that identifies what the different kinds, like which kind of bytes all these bytes are, is just a state machine, very simple state machine. You feed it a byte and then it will transition into the next state. And so what this is doing is I just captured all the states for every byte when I ran it on the code section of this intro. This happens to be a particular conspiracy intro that came out fairly recently. And it just identifies them as like opcode and prefix bytes, mod_rm bytes. I think this is a SIB byte, some 32 bits immediates. There's some displacements as well here. Maybe I'm getting those mixed up, but yeah, so just color codes those, so I'm just able to visually like debug this really quickly. And this weekend I actually finished, at least in the intros that I'm testing with, it seems to work like 100% in the opcodes that I've seen. And that's actually without special casing for some of the opcodes. Like I don't handle enter correctly. I don't handle some other ones, but I'm just not seeing them in the intros I'm working on. So, and the thing is that this doesn't need to be perfect because it's not going to interpret these bytes. It's just going to use them to basically see where it is within the x86 stream and then use different statistics to predict what's going to come next. That's basically all that I'm going to do here, I think. Anyway, there's a lot that goes into this. And a lot of it I'm not going to explain in such great detail, but to give you guys kind of an overview and about what I want to work on today, and I do have to explain some things. And the reason why I'm working on this at all is because I'm working on this in the weekend anyway, and since I haven't been streaming the last couple weeks, I think it's lame if I just don't stream just because I'm working on this. Last couple weekends, that's not why I haven't been streaming. That's for I just needed a little bit of a break. But yeah, I do want to share this stuff. I'm just like on that fence. So if I'm going to be ambiguous about something, just bear with me. But I kind of want to use these streams, and I've said this multiple times to like I don't want to just do something else other than what I'm already working on the streams. I just kind of want to just share stuff, and just like continue on the stuff that I want to work on. And then in addition to that, stream it wherever possible. So probably a bit of a long intro, but that's what I'm thinking. So I think I'm going to draw a quick little thing too, just to kind of give you guys super basic idea what I'm doing here. In Paint, because I think that's cool. By the way, howdy guys in the chat. Kulash, Skeleton, Metal Voids, Local Hoster, The Tourist, Alkama, Soding. How's it going, guys? So to give you guys just like super high level overview, what I'm working on right now is just the packer part, right? So we have, hey Daniel Collin. So we have in an executable packer, we're going to take in an executable, and this is going to have like a bunch of different sections in it that have different pieces of stuff. And we need to basically extract these sections, and we're going to merge them into like another section. It's going to look something like this. Just throwing this together. And it's going to have some other stuff in here, some metadata here that's going to end up in here, blah, blah, blah. Point is, we're going to rip out some of that stuff, end up with this kind of thing here. Then we're going to compress that into this hopefully smaller thing. And then we're going to repack that into an output executable that has the compressed stuff and some other headers. Right? So how pro is this, guys? This is our process. Now, the part that I'm working on today is specifically related to the compression stuff. So that's here. This is the stuff I'm working on. Don't need to save that. And in particular, there's kind of some nice, like there's different pieces of that problem. So we're going to assume that we just have a big binary blob. And this, we know a little bit about what's in here. Like we know that there's an area in here, for example, this, which is going to be x86. And we're basically assuming that we don't know what the rest is, but that it's binary data. And we're going to be doing, Tura says, why not start with the OBJs, by the way? That's a workflow decision. It's a lot easier to drop in a linker in 64K, or sorry, in 4K than it is in 64K. I guess not that hard if you're using Visual Studio, but yeah, I don't think it would gain us that much. Like when you're dealing with 64K versus 4K, it doesn't sound like it's that much more data, but in terms of the uncompressed size, it really is. So you actually don't want to be doing things like slicing and checking those because it's going to take like days every time you do that. So it just makes sense to just use the output executable. It's not really a problem. At the kind of level that we need to compress at, having a good compressor is going to do way more for us than being able to move around the data a little bit more effectively. Because that's really the only thing you would gain is if you do this as a linker rather than as sort of processing the executable. So that's roughly why. But yeah, so this is basically what we have as our input, and then as output, it's just going to be another binary blob that's hopefully denser. Drawing extra lines to show that it has higher entropy. So basically the way we're going to do this is we have different stages. So we're going to have something, we're going to treat this as a big stream of bits, right? Let's actually ignore the fact there's some x86 in there. That's just more to tell you that I kind of know a little bit about what's in here, but mainly it's just a stream of bits. Big old stream of bits is what this is. So something like this. Exactly, localhoster. Might take infinite time to decode, but you know, black hole could pack pretty well, I think. So we have a stream of bits, and basically what we're going to do, we do have some assumptions about probabilities, but that's only here, and we're going to kind of ignore that, like, assuming we kind of don't. We have a stream of bits, and what we need to do is for every bit, every position here, we're going to sort of figure out what the probability, like, we're basically going to run across the stream. At every position, I should say, rather, we're going to predict, we're going to have a model that has seen the previous bits. So let's say we're going to encode this bit here. We have a model that has seen these other bits, right? It's some function of the previous bit. So we could call these H, which is kind of a bad name because that has to do with entropy, but bear with me here. So it has seen H, and it's a model. So our model is going to be a function of H. And it's going to give us a prediction in the range 0 to 1. And 1, it's going to be the prediction that it's going to be a 1-bit, basically, right? So what we have to do is we take some of the previous input, and we determine how likely it is going to be a 0 or 1. So if this is going to be 0, then we basically know for, like, we're very sure this is going to be a 0. Then this history function here from our model is going to give us 0. If it's going to be really sure that it's a 1, it's going to give us 1. Now, in practice, it's not going to give us exactly those, but you can kind of see the idea. And then it's going to predict this. Now, the encoder is going to take that prediction and then encode this somehow. And then the decompressor is going to decode a bit somehow using this. And yeah, should have probably thought more about this before trying to describe it. But what I'm trying to describe is that then there's a coder, which takes in more of a box here. See, so if we have a bit and we have a probability that's going to be 1 or 0, and we put those into our coder, we're going to get some kind of output. It's an open interval because precision. Hand wave. Ignore that. So the point is that as we go along the bit stream, we're going to predict whether the next bit's going to be a 0 or 1. And if we can predict that accurately, our coding function is going to produce smaller output. If we can predict that accurately, and if we can predict that... Skeleton, I really need to hand wave over that because I don't want to get into the details of the coding function. So I'm sorry, you're just going to have to be unhappy and dissatisfied with that explanation. But the point is that if P can predict both accurately and confidently, so for example, if it thinks it's going to be a 1, it should be like really close to 1. If it thinks it's going to be 0, it should be really close to 0. If it can predict accurately and confidently, then our coder will give us smaller output here. If it's inaccurate, or if it predicts like really confidently in the wrong direction, it's going to expand the bits that it's compressing. So the main thing that I want to impress on here is that this part here, our model, this is our magic guy. This is where all the interesting stuff happens. Of course, the coding function is somewhat interesting, and when we talk about things like arithmetic coding or ANS or Huffman or any of those, that's actually the coding thing here. That's sort of this detail here. Let me use a different color for that. That's sort of these details. And then the bit stream, of course, is our input. That's just a stream of bits from our input. But the thing here, predicting probabilities, that's where we're going to spend most of our time and effort when we're building a packer like this. Does that make sense? So what might one of these look like? I'm getting a bit carried away here, but I think this stuff is kind of fun to describe. So we can, if we have this kind of picture here, we can kind of look at like, how might we predict a sequence of bits? So one way to do this, and this is kind of the simplest one you can do that actually does surprisingly well for how simple it is. Let's say we just have a number. So we can call this, I don't know, some model. What do I want to call this? Let's just call this P for our predictor. And it's going to start at 0.5. Right? This is within our 0 to 1 range. And what we're going to do is it's going to see a sequence of bits as we go in. So initially it's going to say 0.5. So in the first bit, it's going to predict 0.5. So whatever we encode, if we predict 0.5, it won't expand or contract the bits. So we won't get compression or decompression. We'll just get like the same. Like the output bits may not look the same because of the way that they're encoded. That all depends on the encoder. But we won't get any expansion or compression of the data. It's just going to be the same size if we predicted this. So if this were static throughout the entire stream, we would get a different stream, but it would be the same size as our input. But what we can do is very simple. Whenever we hit a 1 bit, we're going to adjust this slightly. So we're going to, for example, P0, which is at position 0. This is slightly wrong because this is the prediction that's going to be 1. We can say at position 0. Let's do that. Actually, let's just go with this. Let's just say P0. And then at this position, it's going to be P0. At this position, P1, and so on. So the notation's kind of confusing in my bad handwriting. Mouse writing doesn't help, but you can kind of see where I'm going with this. So after we've seen that this was a 1, we can adjust P1 to be P0, but adjusted towards 1, right? So we could say, okay, that's going to be 0.6, right? And then it sees another one. So then P2, right, is a function of P1 and the previous bit is going to be 0.7. Sure, we can call the probability of it being a 0q. But like you shouldn't need to think about it. We're about the probability for 0 because it's sort of implied here. Just think about the probability one here. But do you see how that would kind of change over time? And then here it would have seen a 0, so it would have predicted with like that it would be a 1 with not that much confidence, and then it saw a 0, so it's going to go back down a little bit here. Now this update function here is just like adding 0.1 depending on what the last bit was. Not a great encoding function, but my point here is that if you just sort of take the previous one and you just kind of like average it, like a really good update function is that Pn is going to be Pn minus 1 plus B over 2. And then B is going to be whatever the actual bit was. This is actually a pretty good one if you just want a super general model that is adaptive and does okay. Like this is about this as simple as you'll get, but still get something decent. Localhosts are a bit off topic, but encoding the x86 or 64 spec in your function and then adding some bits of real-world exe elfs would somewhat help. Maybe, for example. An advantage of that is that you would, for example, be predicting what the next bits are going to be based on stuff you've already seen, like stuff in the real world, like actual symbols, or actual sequences. So maybe that does really well. A disadvantage is that you'd have to have like that dictionary of patterns encoded somehow in your executable. So maybe that doesn't help. But I don't know if that would work really well. That's just kind of the really vague answer to that question. But that's the kind of interesting things that we could experiment with when doing a packer like this. But I think what this illustrates too, though, is that we're going to use the prediction to predict the next bit and encode or decode that, right? And then we're just going to make the next prediction based on the previous prediction and the previous bit. So it kind of makes sense. The tourist says there's a variant of PAC that's optimized for x86 x64 code. As far as I know, PAC does something really interesting, and I'll get to that because I'm using something very similar to that. But a little bit more on this track. The point is that you can make a model like this and it would do fairly well. But for example, you could do something like Pn is Pn minus 1 plus B over 4. And this, there we go. And if you compared these two, you'd end up that this one will, as it sees zeros and ones, this will kind of vary a lot like this, whereas this one will sort of vary less. You see what I mean? And so this one would favor sort of longer streams of bits that it would see, sort of the same data over time, whereas this one would change more to local data. And as it turns out, different ones of these would be better in different parts of the stream, typically. This is what we see experimentally, is that these both do better in different periods. So moving over to something like what PAC does, that's PAQ. It's just a family of compressors that's really, really good, but very, very slow. What PAC does is something they call it context mixing. You should really call it model mixing. But what you can do is you can take these two predictions. So like, let's say this was, I want to call these different things. We can call this model 1 and model 2, right? So let's say this is model 2, this is model 1. And what you can do is you can take the outputs of these. So for example, we can take model 1 times weight 1 plus model 2 times weight 2 and make that your prediction. And then what we can do is we can adjust these weights over time. So if we know that, for example, this one's consistently wrong, we could give it like a negative weight. And if we knew that this one was consistently right, we could give it a weight that's like proportional to how good it's doing. So again, then you would have here with these weights, you'd have feedback similar to something like this, for example. But again, these models could be like any kind of function of the previous input. And it turns out that this is sort of what Pack does. And then to speak to that question, or that comment that the tourist made, is that there's a variant of Pack that's optimized for x86 or x86-64. What they actually do is that one of these predictors here is actually something that models x86 and tries to predict what's going to be next. So it's not, as far as I know, there's no version of Pack that's specifically optimized to do that. They tend to mix several of these models, like on the order of hundreds of these per bit. And one of those just happens to be optimized for x86. So you kind of see where we're going with this? We could predict in different ways, and then if we mix these predictors and we have these weights that are dynamic, we tend to do the best. Now, something like Crinkler, which is the 4K compressor that we use a lot in the demo scene, is also doing this. So what they do, this is kind of getting into the specifics of how their models work. So a Crinkler model, basically what they do, they have a big old hash map. And they look at the last 8 bytes. Not the last 8 bits, but the last 8 bytes. And a little bit more than that. So they're encoding a stream. And they have the last 8 bytes. So they take the last 8 bytes, and they also take the last bits of the current byte that they're looking at. So it's kind of not necessarily to scale. So they're basically predicting, for example, this bit of the next byte. And what they do is they take all of this information. They take which position they're at here. They take all these 8 bytes. And they also will mask off some of these, only use some of these bytes. This is what each one of their models might look like. And so it's going to hash all of this stuff together, for example. All this blue stuff, it's going to hash together, and we get a hash H. That hash is going to be looked up into this big old table, this big old hash map. So let's say it corresponded to here. And what this points to is a cell with 2 bytes. And this is going to be the counts for 0 and the counts for 1s, right? And so if it's seen this context before, so if it hashes this last stuff here, then let's say it saw 1 6 times after that and 0 1 time after that. Then what it's going to do is it's going to basically make a prediction based on this. So for example, in this case, it's going to be, I don't know, 0.9 or something, just to fudge whatever that would be for your prediction. And then it's going to weight it with a static weight that was also attached to this particular model. And what they do is they store, I think they run about 30 of these per bit. And the difference is that which parts of this they encode determines what the model is. So they have a 1 byte bit mask here. That's where it's 1, they're going to hash that byte in the history, otherwise they're not. Just with a bit pattern here. So something like this. And so all of their models have this bit pattern and then a weight that's associated with the counts, actually, I think it is. But anyway, they sum all those up for all those different models, and then they make their final prediction based on that. So this is a really nice way to do it because it's very small. And they do some really cheeky stuff like, once you've seen a 1 here, you don't necessarily have to just increment this. You could also do something like, let's say we saw 0. We would increment the 0, and then we would also half this, for example. And that, again, would just adjust how much we favor more recent data versus less recent data. And so what the compressor does is it actually runs over the data stream many times with different versions of these models, a different list of those, and sort of tweaks that and the different weights as well. But in that case, the weights associated with each model are, like the compressor will go and search for a bunch of those, but then they're static at compression and decompression time. And this is just to keep everything really small because it's for 4K. In 64K, we actually do something very similar to this. Pack does something really similar to this. The later versions do some weirder stuff. I kind of don't want to go into the details too much there because it's something that I'm experimenting a lot with, and there's a lot of different sort of variations of these you could have, and I could sit here for 3 hours and talk about just different ways you can do this. But that's kind of what we're doing here. But what I want to illustrate with a model like this is it's only really looking at like the last 8 bytes. sort of, we would call that a suffix of the history. So like as we move through the byte stream and the bit stream, this will of course change as we sort of slide over different bytes. And one of the things that we find with these kind of models is that they do really well up to order 3 or 4, which means like considering the last 3 or 4 bytes, they start to model really well. So they'll find like short patterns like that. But with the longer orders, like 8 or higher, they tend to not do that great. And the reason is that it's all based on statistics that you've seen before. So if you think about like the last 2 bytes or something, there's only 64K kinds of combinations of those last 2 bytes that you could ever see. And when we're looking at a real data stream, which is, you know, several thousands of bits long, several thousands of bytes even, we'll see different patterns of these a lot. And so we'll collect a lot of really good statistics for like order 2 contexts. But we're not going to see, it's like way less likely that we'd see a specific pattern of 8 bytes many, many times. And so the statistics for those are only going to grow, like, let's say the statistics for a 2 byte context were to grow to something like we saw 81 zeros and we saw 6 ones. And so with this, we can describe with pretty good accuracy that the next bit's going to be a 0, or predict with pretty good accuracy. But with these longer ones, just because of how unlikely specific sequences are to appear again, we might get, for example, 2 and 3. And with that, we can't predict with nearly as much confidence. So it doesn't do that well with the higher order ones, but does really well for the lower order ones. And with those being adaptive and with specific update rules, you can do pretty well with these. And the specific branch that I'm working on today is tweaking a lot of those kind of things with models very similar to this. There's also fun stuff you can do, like you can make a prediction based on just these counts, but then that would actually go into a table. So instead of like this prediction just being something like a weighted average of these, you could have that go into a table where like the 2, 3 would be this entry of a table, and then that would map to a specific prediction in the range of 0 to 1. Say it's that much 0, and then this would be adjusted up and down over time depending on how well it did. Like there's so many different positions here that you can sort of inject like learning capabilities. But yeah, kind of got a bit carried away there with how much I wanted to explain this, but there is kind of that kind of, it's really interesting. I find it really fun. And the other thing that I kind of want to impress on you guys when working with this, and the thing that I've really learned after having tried this, is that because there's so many places to tweak, there's just a lot of things you have to try before you get a really good compressor. And even though something like Crinkler can rely on just this one kind of model, in 64K, we kind of can't do that. Even if we run way more of these, perhaps if we gave them more context or whatever, but it just doesn't work out that well because we're just not seeing, we're not able to, it's just not good enough. We're not able to make good enough decisions, good enough predictions to compress at the level that we would like to. So there we do want to do some more crazier things. So what Crunchy does is they have a lot of models like this, and then they also have what are called match models, which is actually what I want to work on today, is implementing that because it shouldn't be too terribly difficult. And that will do better for these higher order contexts. Basically, a match model is going to, at a particular byte position, whoops, did not want to save that. At a particular byte position, we're going to look in the history. So let's say this is the history. Lots of bytes. So here we're looking at like the end of the stream. So we're going to compress the next few bytes. We're going to look at something like this. Let's say this was 6, 7, 2, 1. And we're working on this byte. So what we're going to do is we're going to look for other places in the stream where we saw 6, 7, 2, 1. Let's say we saw that here, 6, 7, 2, 1, 8. Then we want to predict that the next part is going to be an 8. So for all the next bits of this byte, we're going to try and predict 8s until we notice that one of the bits is different. It's not going to work. But the thing is that this, it seems like this would be really equivalent to the last thing I showed, just because this would be, last 4 bytes or something. And for smaller matches, that is the case. Like they're not doing that great. But this can basically go up to like 2,000 bytes worth of a match length. And at that length, like if you have a specific sequence of bytes, if the sequence of bytes before the byte that you're compressing is that long and you have seen it before, it's really likely that the next thing coming is going to be the next thing that was seen after that in the stream earlier. So that's kind of what this is trying to do. Alchemist says, he says Hoffman-like. I think he meant Huffman-like. But even then, I would kind of say that's not really the case. This is more LZ-like, where we're looking for these specific strings of data in the previous stream. Huffman is more being able to do direct symbol replacement. It's not really RLE either. I think this generalizes over RLE. So RLE would be, like this would be able to detect RLE sequences as well. But RLE is more of a transform that would transform long sequences into shorter sequences. But yeah, so that's like the match models. And what Crunchy does as well is they also take the x86 part, the code section, and they do an entire transform on that just to rearrange the bytes so that this match models and then the context models that I described earlier would be able to do their job better on that existing data by sort of arranging it in ways that it should be able to find the patterns better based on general patterns in x86. Now, I like that approach, and it works really, really well because it's, yeah, you end up, it ends up being that you can have simpler models that predict just as well as more complex models would on the raw data. It also ends up being really, really fast, and that's kind of the main benefit of having simpler models is that you can make them faster because we are doing this coding per bit, and it can get really, really expensive. Like if you run, for example, if you take one of these uncompressed blobs from a 64K executable, and you run that through, for example, Pack, you'll get better compression than you would with something like Crunchy, but it'll take like 2 minutes or something to compress or decompress. And that's kind of unacceptable because remember that we have to run this uncompression routine to decompress the compressed code in memory and then run it so that as far as the user is concerned, like this, and as far as the binary itself is concerned, this is like completely transparent. So we need the same bit sequence that we had on the input coming out of that. And for a user, for someone running this demo, it's like the time from when you double click the executable to when the executable actually starts doing its thing, like pulls up the dialog and runs the demo, that would be about 2 minutes, and that's unacceptable. So we do have to care about speed here as well. But yeah, I think that's basically all I wanted to describe. The specifics of how this is implemented on this branch, I don't really want to go over. I'm not really going to try to hide it because it is basically a lot of the stuff that I described. But yeah, I want to hook up some match models into this, and this should actually work out hopefully pretty well. So all I'm going to do here, I think currently as input, my model doesn't have the entire byte history, and we are actually going to want that, so I'm going to have to tweak some stuff here to do this. I'm going to pull this one out of frame, actually. The biggest thing here is that I want to give my compressor some additional information. First of all, I have update functions per bit. I'm also going to do that per byte. But basically, I'm working out of this function that just given a for every bit, it's going to return a probability. The probability that's going to be a 1 in this interval. This is scaled to 4096 instead of 1, just because I'm doing all this with fixed point integer arithmetic. But yeah, just gonna hook up another couple things here. Yeah, so it calls prob to get the probability for the next bit, and then once it actually had the bit in the encoder or decoder, then it's going to update the model with that, and then yeah, stuff like that. It totally is, localhoster. Like, I'm not doing this because we need the space either. I'm doing this because it's been like a teenage dream for me to do a compressor like this. Something else. And like this is just one way that you could do compression. There's so many ways. And there's, like I said, a lot of things I didn't cover, like the coding function and all that stuff. I actually would like to do a blog post on ANS or perhaps a series, because there's a couple pictures that I actually want to draw, which is how I've learned to understand it, because it was really only in the last week that I really whoa, I totally get it. So I would actually like to do a series on that. Could also do a video on it, but I think writing is more appropriate for that, just in terms of what I want to present and how I want to present it. So I'm just hooking up the rest of this to the model, or to the rest of the compressor. I will say the coder in on this branch is not doing very fancy stuff. It's a range coder that normalizes to 24 bits, so it outputs or inputs 8 bits at a time, which mostly has speed benefits and good enough precision. If you don't know what that means, just ignore it. So yeah, so all I did here is just I had an update byte function, so that every 8 bits we'll get all these probabilities and updates, and then after the last one, we'll just get a callback that was the whole byte. Yeah, middle out, exactly. So what I think I want to do is actually make another thing here. So I'm not going to go over that much of what I already have. I do kind of want to go over what I'm writing here, because this might be somewhat interesting. Oh, that's cool, Man Moose. I think it's really fun. Audio and video tend to also have that component where there's usually multiple transforms on the data to sort of quantize out different parts of it, sort of lossy transforms. And then you'll have a more speed optimized way to encode the remaining stuff in a lossless way. I've also been thinking about this for our 64K stuff. We have some sample playback that uses a built-in GSM codec on Windows. And I would kind of like to, since we already have lossless coding in the form of the executable compression that we're doing, and the fact that lossless coder is actually pretty adaptable, it's kind of silly to have both stages on that for the audio data, because that's basically what we're getting as output from the GSM codec. Is it has done some lossy stuff on it, and then it'll do the lossless part. Whereas I'm kind of thinking we could do our own codec that would just do the lossy part, and then rearrange the lossy coded data just so that it would compress well with our executable compressor. Because typically if you take compressed data and you put it through another compressor, it's going to have a really hard time predicting the data in there because it's already so dense. So it usually expands that kind of data slightly. So I'm just wondering if we could do our own codec that would just do the lossy parts and then rely on the on the executable compressor to do the other parts. I think we could actually do really well with that. Also, the GSM codec is not very good anyway, like in terms of audio quality. But we get it for free by just relying on Windows. So I think we don't need to do much here. The other thing I'm going to do, by the way, I'm going to add some more stuff here. Trying to think of how I'm going to architect this. So I'm basically going to have the same kind of interface. Oops, that's going to be in here. Don't know what I need for this yet, but did I just do? Yeah, I did. We don't know better, so I'll make that mutable. Whoops. That's correct, Alcama. Yeah, DCT would be nice and cheap. I think we could do a bit better than that, but it would definitely be a good first step. Actually, we'll do 2048 here. Something like this. Context model hashes. I think I want to do stretched probability out of this. Maybe I don't. We'll see. We'll see. Oh, we're not doing... we're just talking about lossy compression of audio samples, but I'm not actually doing any lossy compression right now. Doing lossless stuff. Particularly modeling of a bit stream. This will be match model. I think that'll be good. Actually, I want to put this here. Reason why I'm separating those mentally, but don't have to worry about that. And just putting this in here. The best thing I can do to make this work is a couple things. So all this needs to do, so match model, update, byte. And here we need to do some funky stuff. Whoops. Dear Green, this is Rust. So this is for executable stuff, but it's just general data compression for 64K stuff. Yeah, we need to do the counts. I used to talk a lot about why I use Rust over C, but lately it's just because it's nice. So I'm doing entropy coding. In particular, I mentioned at the beginning of the stream that I'm being a little bit intentionally vague about some of the stuff I'm doing, but basically I'm doing entropy coding and I'm doing modeling for an entropy coder, and I'm adding a match model that should do LZ-like matches in order to predict probabilities for the entropy coder. Is, I guess, the shortest way I can I can describe that. But yeah, I'm gonna gloss over the whole Rust versus C thing. To be honest, it's not what I want to focus on right now. So I think that's more or less what I want here. Here I want to do that. A lot of things specific to just how this is set up, and just don't worry about it. Frankly, I don't have a good answer for that, Dare Green. I'm using Rust because I'm using Rust. Just please ignore for this task. It's irrelevant. Oh, I bet Mamoose. Well, I mean, I'm comfortable with C2, but I'm using Rust for this. Just so if I just do this, then we'll get the effect of just having a static model. I'm just gonna run this to make sure it is working, hooked up in some sort of way. Yeah. So again, not showing the results, but getting exactly 0 difference by having that model, which is exactly what I would have expected. Definitely should use PHP. Let's see. I think so. There's different ways to implement these kind of match models. I've seen some that use like hash tables in order to get faster, find the matches faster, I'm actually just going to do a stupid search, and it's going to be fine. I think what we want to do is model having a current match or not, and then whether or not it's active. And then each bit, we're going to try and predict the next bit if this is active. Otherwise, we want to output something else. I think I want to do stretched prob out of this. Actually, that doesn't really matter. That's a decision that I'm going to sit here and make on and off until this works. The stretching and squashing, by the way, just so I can kind of describe a bit of that. This compressor is doing a bunch of mixing of different weights, different predictors, different predictions from different models that are weighted. And it actually, it takes, instead of the 0 to 1 range, it puts it into a logarithmic range that's -1 to 1. And it's curved such that it basically stretches out the ends. So that if you output 2048 like 0.5, you actually get 0 contribution to the weighted average. Just some nicer stuff there. It ends up compressing better. I think in 2012, someone actually proved that that's like the optimal space to do this kind of mixing in, because it minimized some theoretical thing that I didn't understand. But that's what I mean by stretched or unstretched, is that like, or stretched or squashed. So we need to say something like, how do I want to do this? Because we basically want to look at the previous input and then see if like the last sequence of bytes that we have matched. So we need something like whether or not we have a match. We need something like match length. In fact, we can even use that for both. And we can just say 0 if we don't know better, and that's fine. And this will be something like 32. Yeah, something like that. And then our probability could be if match len is 0, then we're just going to return this. Oops. This is basically what we're doing, is if we don't have a match, we're going to do this. Otherwise, we're going to predict the next bit in the byte with some kind of scaled prediction. So that the longer the match, the more confidence we are. So let's see. Something like const. Do something like that. And with this, might even be able to scale based on this directly, which could be kind of cool. Although, yeah, I'm not sure what I want this to be yet. And then this is going to look something like this. It's basically it. Just do something like predicted. I need to look at the order that I do this in. He's a hunter. A chief detector. Yeah, so this is basically what the predicted bit is going to be. There's a reason why I'm having this down here. And so then update bit is just going to increase our bit position. Update byte, we're going to want to actually search for the next match. There's also another thing that we're going to want to do, though. And I think that's just going to be simple. If the bit is not what we predicted it was going to be, then I think we're just going to shut down by saying match len is 0. No comment. And then here, I guess an easy way to do this we could just have it go with full confidence, but we do want to scale the confidence based on the length, and we probably don't want that to be linear. We could do it linear though. Self-predicted bit, shift left. No, because we want to do I guess we can do this. Stretch, I believe, was a function on here, so we needed to do it that way. So if we shift left 12, then we'll get to 4096 just from 1. So we can do something like shift left 8. No, we want 12. We'll do this as I32 minus 2048. Yeah, bit pause is probably what I wanted here. I think I used bit index in a couple other places. That's where I got that. In fact, yeah, I'm going to change that. Yeah, because this will scale it to something like 0 to 1 pretty hard. And we can get that signed. And just do something like this. Or I want to scale this. And then just shift it down a bunch. Something like that. So I think this is going to be a really bad predictor. Like this, I don't think is going to be very good. But it does do the things that I want it to do, more or less. And if it's bad, the mixed weights and everything will sort of solve that problem. So I think we'll be okay. But then we want to do the search. And here we actually need like the input and our position in the input as well. So I need to do a little more plumbing here, which is fine. If we have, for example, but we just had something like this. This to be a slice here. And then I need to fix that. Where we're coding stuff. I think this won't be a good predictor, but I think the logic is going to be okay. And take our predicted bit and scale it. Otherwise, if we don't have a match, which is basically what I'm encoding this way, then we're just going to do 50-50. That's going to be fine. And then, yeah, update is going to see if we didn't match what we predicted. And sort of we're not going to predict. Like, the reason I'm doing this is to not predict further bits of the byte if we've seen that it's not correct. And then, yeah, here we can do here we increment the bit index, and that's just going to be reset here on update bytes. So do self.bit index is 0. Yeah, I think this makes sense. So I wanted this to be, yeah, that's, yeah. So I actually did, the packer I did for C64 is an LZ packer, and it's going to do a search. And I think I can just sort of copy a lot of stuff from here. Take that input length. And this does like max distance and max length, which when you're encoding LZ stuff, you actually want an upper bound on those. Not going to need those in this case because we're just looking for the longest match. And then we need the index of that. We actually don't if we just do the search every time, which is going to be slow, but it'll work. So I think we want to do this. Okay, so this is even doing longer matches here. Right, because this was doing that for every bit position. We actually don't need to do that loop the same way here. It's going to be more like this stuff. Yeah, 'cause we already have byte index here. So I think we can just do this. Just match length is 0. And I think we just do this here. Oops. Oops. Just the match length. Probably gonna be lots of type errors and stuff. Not too concerned about that. Yeah, maybe I should have written this from scratch. It actually looks like I found matches before this, and then did I do that? No way. Oh no, this is to find the matches for that, and that's fine. Something like this. Yeah, I'm actually just gonna write this from scratch. Although I kind of like having these. So our search start index, for example, is going to be index -1. We even do while here. Right. So we actually want this even. Start the search there. This is actually going to be the current byte, I think. we'll do this. Start at -1 there. Yeah, so basically this is gonna sit here and increment where our search starts and where we're comparing from. Yeah, I don't think. No, this does make sense because we're going to start at where the byte index was. For example, if it were 1. I think that's actually correct because we'll always find a match of length 1 here, which we actually do want to do. Input length here is not what we actually want to be the end, though. We want that to be byte index. Like that. Yeah, then we'll get our search indices increased here. So then search index, yeah, so then we'll get a match of length 1 in that case, and otherwise they'll be increasing. So I think that's good, and then this will search backwards, so it will take the longest one with priority given to the more recent ones, which is what we want. Length is this, if it's greater than min length, which I actually don't care about minimum length. We're going to do this if the length is greater than this. I think that makes sense. And I think the last thing we do is self dot predicted byte is the one that's here. No, it's actually this one because we saw matches up until there. I'm just thinking of the case where this is 1 again, because that's our degenerate case here. And the max length here is mostly to stop the search from being n squared. I realized that my decoder was wrong because it was passing in the wrong stream here. This we shouldn't need because input here is not really the best name for that, but well, that'll be fine. Just thinking through this again. I think we actually want this. We're going to do this. And then, yeah, our search index is going to be the next byte, which is what we could have predicted here. Just thinking through this again. For our position where, like the last one, for our position where 0, we'd early out here. For our position where 1, we would actually do the search. We would search from 0. This would be okay. And this is fine because we can actually read the byte at byte index, I think. Now I know we can. I think this is basically correct. Yeah, I don't like this loop right now. But if it works, I can make it better. I gotta do some different things here, it looks like. I also want to just try doing this just to make sure that everything runs correctly. Looks like it froze, and it's probably because I fucked something up. We'll get there. The alternative here, though, isn't that bad. I mean, we could just do this. And then just a bunch of casts here. I think another thing I want to do just in case make a max search window so we can early out and see if that helps. Oh, you probably meant this while is the nasty one. That's okay. Because the logic there is not that complex. Okay, I got an out of bounds error. That sucks. Do this just to read it a little better at least. I think that's why. Because that could have caused this to be by index +1 and read this one last time at the end, which would have been bad. So yeah, so now the logic here is correct. Maybe not the simplest, but it's definitely working. My compression tests are running a lot slower now and seeing very little gain from this. Gonna let a couple executables finish and just see where we're at. Yeah, I am actually seeing a tiny bit of reduction already. Like, this did help. Not much, though. And I'm wondering if that's when we start tweaking this. I'm not seeing any expansion, which is good. But, I mean, I'm seeing reduction on the order of like 10 bytes, which is really bad. So a couple things I want to do here. First, I think I want to make this output stretched probability. Which I keep going back and forth on, but I think I do want to do that. Or actually, let me think about the output here. And it might also be interesting to print like what the greatest match length was. Although I'm guessing we might saturate here because I know that there's some cases where we're going to go through big ranges of like all zeros. And we're probably going to hit the search window length. Yeah, no expansion yet, just seeing, I think the most I'm seeing reduction here is, oh, no, there we go. Reverence got 3 bytes bigger. Okay. So we have our prediction and we have our match length. We hit this, we want it to be really confident. A really easy way to tweak this is just make it more confident. And I'll have to think more about like, yeah, probably just have to sit here and think more about how I want this to be and start playing with different kinds of functions here, because like this is just some crap linear stuff based on the length, and I know it's not very good. But even just sitting here playing with this, we can actually, I do actually see some improvement. Not much though. Although, did get through what I wanted to get through today, even after taking more time than I expected to explain some of this. The other thing that I will probably do is dig into like Pack and some other compressors and see what they're doing to get their predictions from their matches. Because like the way that we're searching, this can be improved to improve speed, but it's still going to be the same kind of, like the idea is going to be the same. We're going to search for the longest match that we can, and we're going to use that to predict what the next bit's going to be. And if we're wrong, we're going to drop the prediction. Like it's that simple. But then like what our prediction looks like and how confident it is, we're going to want like some special curves, some curves tweaked to those kind of lengths. So I think it'll be a bit of experimentation there and a bit more digging into other resources, see what they figured out. But yeah, I think I'll continue that on my own. I'll call it a day for today. It's already been an hour and a half. But yeah, here was a small window into some of the compression stuff we're working on. Anyway, thanks guys for hanging out. I'm going to head out, and I'll see you guys next time.